Hello, I'm Nicholas Dwork, and this talk is about utilizing the wavelet transform structure in compressed sensing. Compressed sensing amounts to solving this basis pursuit denoising problem, where we're minimizing the L1 norm of our optimization variable subject to the difference between AX and B being less than some error epsilon. And when the matrix A satisfies certain properties, then solving this basis pursuit denoising problem also solves the corresponding sparse signal recovery problem. Whereas the sparse signal recovery problem is in general NP-hard, this problem is a convex optimization problem. It is tractable, and it can be solved with known algorithms. With MRI, the problem we want to solve is minimize the L1 norm of WY subject to the difference between our MRI system's output and our measured data being less than some error epsilon. Here, the matrix W is the sparsifying transform, and the discrete Debouchet wavelet transform has been shown to be an effective choice to sparsify natural images. The matrix F is the discrete Fourier transform, and the matrix M is the sample mask. So this is the problem that we want to solve. If we let X equal WY and A equal MFW inverse, then we're back to this basis pursuit denoising problem. And in this case, A satisfies the restricted isometry principle in levels with high probability. Okay, so here's an MR image of a knee, and we're going to take the discrete Debouchet wavelet transform of this image. Here's the magnitude of the wavelet coefficients, and you see that it is indeed more sparse than the original image. There is much more black in this image than there was in the original. However, we see that the upper left-hand corner of this result is still not sparse. And so we could apply the wavelet transform recursively to increase the sparsity of the result, as I have done here. There's a part of this image that is not sparse. If we look at the upper left-hand bin of this image, we see that it is indeed not sparse. This is a low-pass filtered and decimated version of our original image. And in general, low-pass filtered natural images are not sparse. Here are 5 different examples. The second row shows the magnitude of their wavelet coefficients, and if I zoom in, indeed none of these images are sparse in the lowest frequency bin. So this motivates our approach. What we're going to do is start out by reconstructing the low frequency portion. And since it's not sparse, we're going to rely on the Nyquist-Shannon theorem. And so this will dictate the size of a fully sampled region in the center of the Fourier domain that we will collect. And if you just inverse transform the coefficients attained in this low frequency region, you get the commonly observed Gibbs phenomenon ringing. So to mitigate that, we can apply a Kaiser-Bessel window, which eliminates much of the ringing that we previously saw. Okay, so we've got an estimate for the low frequency portion. Then we're going to subtract that low frequency portion out of the data and then reconstruct the rest relying on sparsity. So here's the result of taking these original 5 images, subtracting out the low frequency portion, and then looking at the wavelet coefficients of the results. And if we zoom into the upper left-hand corner, we see that this is much darker than it was in the original images. Okay, so this is the problem that we're going to be solving, where Y hat L is the low frequency estimate, KB is the Kaiser-Bessel filter, and F star is the adjoint of the discrete Fourier transform. And through a similar set of variable definitions, we end up again with a basis pursuit denoising problem. And the only difference between this problem and the one I showed you previously is that instead of being the L2 norm squared of AX minus B, it's now the L2 norm squared of AX minus beta. The matrix A is the same. So if the previous matrix A satisfied restricted isometry principle and levels, this one will as well. So we're going to try reconstructing images using the original basis pursuit denoising technique and this new technique of more sparse basis pursuit denoising, both with and without a fully sampled region in the middle. The top row shows the basis pursuit denoising result. The middle row shows when the fully sampled region is included, and the bottom row shows the result of this more sparse basis pursuit denoising problem. In general, more sparse basis pursuit denoising attains the best results. Here's zooming in to just 8% of the samples, and if we zoom in just into the kneecap, you can see that the more sparse basis pursuit denoising result is the most detailed. Here it is for all 5 images. When 8% of the samples are used, the more sparse basis pursuit denoising generates the most accurate reconstructions. Okay, so we have taken advantage of the Debouchet wavelet transform structure, and this allows us to generate quality images with less data. Thank you for your attention.